Okay, in this problem, we are given the three capacitors C1, C2, and C3, and they are connected across a 9-volt battery, and we are asked to calculate the charge on each one and also the voltage or the potential difference across each of these capacitors. So we want to draw a series of diagrams here. We'll first recognize that these two are in parallel because the potential difference across both of them is the same. So we can write this down as this is equivalent to the battery connected to C1 and the parallel combination of C2 and C3. I'll call this C23. That's this one. And this is C1. So C23 is the sum of C2 and C3 because they're in parallel. So it's 2 plus 8, which is 10 microfarads. Right? So this is a 10 microfarad capacitor, and C1 is given to be a 5 microfarad capacitor. And once we recognize that these two are in series, we can put them together and get an equivalent capacitance. So if I do that, I've got an equivalent picture of the 9-volt battery connected to a single capacitance. Right? That's your C equivalent. And the C equivalent, since it's the series combination of C1 and C23, I can use the formula for the series equivalent. 1 over C equivalent is 1 over C1, which is 5, plus 1 over C23, which is 10. And simplifying this, I get C equivalent to be 10 over 3 microfarads. Right? So you have a 10 over 3 microfarads connected across a 9-volt battery. And the idea here is in all these problems where you have to find the charge, you always work from the very last picture first. Figure out what the charge would be on the equivalent capacitance. Right? So if I call this a Q, that's the charge on the equivalent capacitance. And then you go back to the diagram before that and you recognize that C1 and C23 are in series, which means they should have the same charge, which is the charge on the equivalent capacitance. Right? So the charge on C1 will be Q and charge on C23 will also be Q. And finally, you come back to the original diagram here and you recognize C1 has charge Q. Let me write it. This is Q. And the Q on C23 is really a combination of Q2 and Q3. Right? So I can write the charge on C2 to be Q2 and then the charge on C3 to be Q3. And it's easy to see that if you add up Q2 and Q3, you should get the Q that's on C23. So starting with the last diagram, we can write down the charge Q on the equivalent capacitance using the definition of capacitance. Q is capacitance times delta V, and the equivalent capacitance is 10 microfarads times 9 volts, and that gives me 30 microcoulombs. Right? So 30 microcoulombs is the charge on the equivalent capacitance. Right? So this has 30 microcoulombs. And if we go back to this, right, if you look at this one here, that means there is a 30 microcoulomb on this, right? This is 30 microcoulombs and a 30 microcoulombs on this as well. So we already know the charge Q1 on C1, that's the 30 microcoulombs, right? And we need to get the charges Q2 and Q3 now. And we do know the Q across the combination of the two. So I'll just give this some name here. I can call this points C and D, right? Points C and D. And if I figure out the voltage across points across this C23, that's the delta VCD, or I can call it delta V23, right? So if I do that, I can write this one. I can say delta V23, right? That's the potential difference across C23 is Q divided by C23, right? And Q is 30 microcoulombs divided by C23, which was 10 microfarads, right? So the micros cancel off, and this gives us 3 volts. Right? So this is the voltage across C23, right? So there is a 3 volts across this, and the total is 9 volts. So 6 volts must be across C1 and 3 volts across the 10 microfarads or the C23, right? So, so getting back here, that's the voltage across both C2 and C3, right? And since they are connected in parallel, each one of these, C2 sees a potential difference of 3 volts, C3 sees the same potential difference of 3 volts, right? So I'll just put it here for our, so the potential difference across this combination is 3 volts, right? So I can calculate Q2 as C times delta V. So C2 is your 2 microfarads times 3 volts, right? You multiply the 2, you get your Q2. And similarly, Q3 will be C3 times the 3 volts across that, right? So putting it all together, I can say that Q2 is equal to C2 times delta V across C2, which is what we've called delta V23. And since C2 is 2 microfarads, right? So this is 2 microfarads times 3 volts. So Q2 comes out to be 6 microcoulombs, right? 6 microcoulombs. And similarly, you can calculate the charge on C3. C3 times the voltage across C3, which is delta V23, right? So C3 is your 8 microfarads times 3 volts, and that gives you 24 microcoulombs. And you can quickly check that if you add up Q2 and Q3, you should get the 30 microcoulombs, which was the Q on the equivalent capacitance, right? Putting all the results here in this table, you can just make a little table with the capacitor values C1, C2, and C3, the charge on each one that you calculated, and the delta V across each one. And if they ask you to calculate the energy stored in any of the capacitors, you could use the corresponding formulas, either 1/2 C1 times delta V squared or Q times delta V will give you the energy that's stored in C1, and so on and so forth.
Made with Doodlecast Pro.